So in analog to digital conversion, as I was telling you in the earlier class, that uh, we need to follow certain processes in order to convert a analog signal to digital. Those processes are your sampling, okay, then after sampling you have to do quantization, and then the third process is encoding. Okay, so the output of these three processes is actually the digital signal. So analog signal is the input and the digital signal is the output. That is how this process actually works. Okay, now what is sampling? Sampling is the process by which we convert a continuous time signal into a discrete time signal. You already know what is a discrete time signal, right? In the first like in the first module we have already discussed what is a continuous time signal and what is a discrete time signal. Okay, so we convert a continuous time signal into discrete time signal, and that process is actually sampling. Okay, so once we convert that signal into a discrete time signal, still the amplitudes are still continuous. Okay, although time is discrete now, time is discrete as you see here. Okay, if this is your, let's say, t0, this is 2t0, this is 3t0, likewise, but amplitude still continuous. Okay, the amplitude that you will be getting here will be from a continuous range of values, which will be from minus infinity to infinity. Now that is a big problem, so we have to round these values. As you have decimal numbers now, 1.2345, you try to round it to some, let's say, one decimal place or two decimal place, you normally try to round it na? So that process of rounding is this quantization is the process of rounding. So the amplitude will be something, let's say, 1.1234, we will round it to 1. Similarly, let's say the amplitude is, let's say, 1.23, let's say something like this, 435, like this. So we could round it to, let's say, 1.5. In this way, the process of rounding is actually the quantization. Try to understand this. And encoding is actually a very simple process, where what we are doing, we are allocating a code to these amplitude levels. Let's say amplitude is 1, the code will be 0001. Similarly, amplitude is 1.5, the code will be 000010. This could be like this. You could allocate a code to a amplitude level, and that is the process of encoding. Okay, so now let us discuss these processes in detail. So first is your sampling. Okay, so we already know that as we have already discussed, that our analog signals, if you have analog signals, they can be digitized through sampling and quantization. So you could note it, that can be, analog signals can be digitized through sampling and quantization. Okay, okay, so analog signals can be digitized through sampling and quantization. Then what is sampling? So sampling is a process which you could note, that sampling is a process that converts time signal, continuous time signal to discrete time signal. Okay, so the definition is clear. Sampling is a process that converts continuous time signal to discrete time signal. Okay, so the however, there should be a rule that we should follow. Okay, that is, the sampling rate must be sufficiently large. Okay, must be sufficiently large, so that the analog signal can be reconstructed from its samples, from the samples. Okay, with sufficient accuracy. Okay, so this point is very important. that the sampling rate must be sufficiently large so that the analog signal can be reconstructed from the samples with sufficient accuracy. Now, let's say you have an analog signal like this, okay, and you want to digitize it. Okay, obviously the first step would be sampling. So how many samples would you take? Let's say here in one cycle I am taking, let's say here 6 samples, as you see, 6 samples. But are 6 samples enough? See, when you will be you have converted this analog signal to digital, okay, into discrete, huh? Let's say discrete. Then you could convert it into digital also. So you have converted your analog signal to discrete. Now, obviously, when you will be playing back this signal, okay, this way you will be transmitting this signal. So once it has been transmitted, the receiver will be receiving it. Okay. So once the receiver is receiving it, the receiver has to reproduce that signal from those samples. From these samples, the receiver has to get back the original signal, which was like this. But are these samples that I have taken here, are these samples actually enough to recreate the signal? One thing that we can all agree is that if I increase the number of samples, let's say the same signal is there, same analog signal is there, I am increasing the number of samples. Okay, and you could see, you could compare both the cases, that when the number of samples is higher, obviously the signal that will be recreated will be of higher accuracy, right? This signal will be of higher accuracy compared to the previous signal which will be recreated. All of us can agree on this, right? However, what rate is actually a minimum rate which we should follow to sample a signal? Okay, so there is a minimum rate at which we should sample the signal, and that is given by the sample. Okay, so you could increase the sample rate to any value, but there should be a minimum sampling rate. So lower limit is at least is very much important here. Although higher limit you can take according to your choice. Okay, or the bandwidth available for transmission that would decide this. However, there's a lower limit that we should follow. That is how many minimum samples we could take from a signal. Okay. So sampling theorem actually provides that minimum rate. Okay. And it is like this. The sampling theorem says, okay, that a signal whose spectrum, okay, band limited to capital B Hertz. Okay. A signal whose spectrum is band limited to capital B Hertz. That means, in other words, that is Fourier transform G of omega is equal to 0 for your omega mod is greater than 2 pi b. Okay, that means this signal exists for this much amount of bandwidth. Okay, and outside that it doesn't exist. So can be reconstructed. Okay, exactly, can be reconstructed exactly. Okay, that means exactly means without any error. Any error. Okay, from its samples. Okay, taken uniformly, taken uniformly at a rate capital R, okay, should be greater than equal to 2b hertz. Okay, later on we will be seeing that this equal to 2b hertz will not be possible. Exact rate that we will require is greater than 2b hertz. Okay, for practical conditions. Theoretically, okay, R should be greater than equal to 2b, but practically, okay, you should require your R greater than 2b hertz, where R is the rate at which samples will be taken. Okay, which also means if a signal bandwidth is, let's say, 1 hertz. Okay, 1 hertz. 1 hertz means 1 cycle per second. This is 1 cycle and this is 1 second. Okay, that means for 1 hertz of bandwidth, okay, you will be taking greater than 2B hertz. So at least 2B, that means at least these two samples, okay? And at max, there is no max limit. At least like under theoretical conditions, you should take two samples, and in practical conditions, greater than this two number of samples. That means you should take three number of samples, four number of samples, five or something like that. Okay, so it should be the rate of samples should be greater than 2B hertz practically. Then only the signal can be reproduced from this sample. Okay, so it should be taken at a rate capital R, and the unit will be in samples per second. Okay, so is this clear, this theorem, sampling theorem, or any doubt here?
Yes, sir.
Because once this is clear, we can proceed to the next part. Okay, so in other words, we could also write that the minimum sampling frequency is how much? Your Fs is equal to 2B hertz. This is the minimum rate at which you should sample a signal, or this is the sampling frequency. That means if a signal is of 1 hertz, okay, that means 2 into 1 hertz, that is 2 hertz should be the minimum sampling rate. Okay, so Fs should be minimum of 2 hertz, maximum it could go to any value as per your system can process. Now let us prove the sampling theorem. Like why we should follow this kind of sampling theorem, let us prove that. Okay. This proving the sampling theorem is actually a part of the question that normally comes in the examination. They normally ask state and prove the sampling theorem. Okay. So to prove the sampling theorem, okay, let us consider a signal g of t. Okay, signal, and we have named it g of t, and we can draw that also. The signal g of t will be like this. So the signal g of t is like this. Okay, so this is your g of t, and it is assumed that the signal g of t, this is the signal g of t, this is figure A, let's say, and the spectrum is band limited to B hertz. Okay, let me write that here also, whose spectrum is band limited to capital B hertz. Okay, so the spectrum is band limited to capital B hertz. That means in the frequency domain, this signal, this g of t would look like this. This is the spectrum, this is 0, okay, and the signal will be like this. So this is your 2 pi b, on the other side this is minus 2 pi b, okay. So that means the bandwidth is b hertz and the amplitude here is a, okay, which also means that here the amplitude is a, this signal g of t, the amplitude is a, okay. So we are taking a signal like this, and then we will be sampling this signal, okay. So let's see. So sampling your g of t, at what rate we will be sampling? At a rate which is your Fs hertz, okay, and that means it can be written as Fs samples per second, okay, and it can be accomplished, okay, can be accomplished by multiplying g of t, okay, by an. So what we could do is that if we multiply this signal by a impulse train, we can sample it. Okay, so exactly the same thing I am writing here can be accomplished by multiplying g of t by an impulse train. Okay, impulse train, a train of unit impulses, impulse train, and we will denote that train as delta ts of t. Okay, so this will be consisting of your unit impulses, okay, repeating periodically, repeating periodically every ts seconds. Okay, every ts seconds. Why ts second? Because we know that time and frequency are reciprocal of each other. That means ts is equal to 1 by fs. So whatever the sampling rate you take, its reciprocal will be the time ts. So that means we will be multiplying a impulse train like this, which we will be writing as delta ts of t, and it will look like this. It will be impulse train like this. Okay, and these impulses are exactly located ts seconds apart. And this means this width that you see here is ts seconds. Anywhere else also, if you check, the width will be exactly ts seconds. Okay, now, so what we are doing here, we are multiplying this impulse train with this signal g of t. Okay, so if we multiply both of these signals along with this, if we will be multiplying, let's say, this signal, I am redrawing it. So this is this dotted line shows us the envelope of the signal to which we will be multiplying. Okay. So if we multiply it, let's see how the signal would look like, how the output signal would look like. So if we multiply these two, the output signal will be like this. According to the envelope of this baseband signal, okay, the amplitude of the impulses could be changed. That means exactly at these locations we will be having the impulses, but their amplitude would have changed according to the amplitude of the baseband signal. So we will be getting the signal like this. Okay, so this is the signal we will be getting. So we were naming that signal g bar of t. The sample signal we have named it g bar of t. So let me write that also here. The result of uh, multiplying g of t with your delta ts of t is shown here. Okay, so here also one thing that you should note is that distance is still ts. Okay, whereas the amplitude has changed. The distance between the impulses is still ts, but the amplitude has changed according to the g of t, or nth impulse you could say. Nth impulse which is located at your nts. Okay, t is equal to nts, has a strength, how much, g of nts. This is in accordance with the property that we had discussed in the first module basically. Okay, so that is the value of your g of t at your t is equal to nts. Okay, which actually means this, if we consider the nth pulse, so let's say this is the nth pulse. Okay, then what is the time here? It is nts. Okay, so what is the amplitude here? It is exactly the amplitude of your g of t at that time. Okay, so at that time, what is the amplitude of g of t? It is g of nts. Is the amplitude of g of t at that location. Okay, and this is in accordance with the derivations that we did in the chapter 1, exactly according to that. Okay, so now that we have got this sampled signal, okay, so let us do one more thing. Let us try to find out what is there in the sampled signal. Okay, so the sampled signal is like this, g bar of t, and how we have got it? By multiplying your g of t with delta ts of t. Okay, so we could always write it in this form. See, if we consider that the strength of the impulse located at t is equal to nts is g of nts. Okay, so we could write it in a different form, in the form of a summation. Okay, summation of n. Okay, so g of nts, okay, multiplied with del of t minus nts. Okay, so del of t minus nts actually means a shifted impulse. So del of t minus for the different values of t uh, and n, we would get actually these shifted impulses like this. Okay, so shifted impulses, and how, what is their strength? Their strength is G of NTS. Okay, so for n is equal to 1, it will be T minus 1 TS, right? T minus del of T minus 1 TS, and this is G of TS. So that means the first at your T is equal to TS, whatever is the amplitude of this signal. Okay, so at TS, what is the amplitude? At 2 TS, what is the amplitude? At 3 TS, what is the amplitude? That is of relevance. Okay, so we have, that's why written it in this form. Okay, now what we want to do is we want to expand this signal, and we would like to visualize what is there in the spectrum of this signal. Okay, so here if you see your del of del TS of T, this impulse train, okay, is a periodic signal. If you note it, it is a periodic signal. Okay, what is the period of this periodic signal? They are occurring every TS seconds. Okay, so their period is TS. Okay, is a periodic signal of your period TS. Okay, so that's why it can be represented in expressed as Fourier series. It can be expressed as your Fourier series. So let us express it in the Fourier series. I'll be directly using a result. Okay, so the trigonometric Fourier series is how much? It is this much. Del TS of T, only del TS of T, okay, is equal to how much? 1 by TS. I have directly found it out. You could also verify it yourself. You could directly find Fourier series also. You have already found the Fourier series of an impulse train, although you had found out the exponential Fourier series. Okay, you could always find the trigonometric Fourier series also. So if we find the trigonometric Fourier series, we would get this much. So 1 by TS times 1 plus 2 cos omega st. Okay, that plus 2 cos 2 omega st, that plus dot then next, let's say plus 2 cos 3 omega st, and in this way dot 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 dot. Okay, where we already know that omega s is equal to how much? 2 pi by ts. Okay, because fs is equal to 1 by ts, that's why. So which is also equal to 2 pi fs. Okay, so now what we could do is we could directly replace this del ts of t, okay, with this Fourier series. Okay, let us replace it and see how this equation actually looks like. So therefore we could write it like this, that our g bar of t is equal to how much? Your g of t multiplied with delta ts of t, del ts of t, which is equal to 1 by ts times, okay, just look at this previous equation. Okay, we will be using this here. Okay, so how much we have? 1 by ts times, okay, 1 plus is there, so this g of t is multiplied with it, so with this delta ts of t, so we will be writing here g of t, okay, that plus 2 g of t cos omega st, okay, then again that plus 2 g of t, third term 2 omega st, 2 omega st, that plus again 2 g of t cos 3 omega st, in this way, that plus dot 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 dot, this goes on like this. Okay, now if you look at this equation clearly, okay, and you would like to find the Fourier transform of it, you could easily find it out. Okay, if I take the Fourier transform of g of t is g of omega, okay, the Fourier transform of g of t is g of omega, right? That means I can write that g bar of t after Fourier transform is g bar of omega. In the same way, I could express the other terms also. Okay, this g of t cos omega st is there. So cos omega st can be written as e to the power j omega st plus e to the power minus j omega st whole by 2. So this 2 will be cancelled. Okay, so this g of t let me write it here, g of t cos omega st, 2g of t is there. So that can be written as 2g of t, okay, multiplied with e to the j omega st plus e to the minus j omega st whole by 2. Okay, so you already know what is the Fourier transform of g of t multiplied with e to the power j omega st, because you already know that the Fourier transform of g of t is g of omega. Okay, similarly for g of t e to the power minus j omega st, you also know what is the Fourier transform. What is it? Can you tell me? Just use the frequency shifting property of the Fourier transform and just tell me now how, what will be the
So
Fourier
G of
transform of
omega
this.
minus omega s.
Yeah, g of omega minus omega s. Similarly, for the second term, it would be g of omega plus omega s. Okay. In the same way, if you see, we have other terms also, right? You see, here we have other terms also. G of t, 2 cos 2 omega st. Sorry, I think left cos somewhere. Cos 2 omega st. Then cos 3 omega st. In this way, we have different terms. That means we will be getting these spectrums, which will be here g of omega minus 2 omega s, g of omega plus 2 omega s. Similarly, for the 3 omega s term, we will be getting g of omega minus 3 omega s. Similarly, g of omega plus 3 omega s. In this way, we will be getting so many terms up to infinity. We will be getting infinite number of such terms. Now, we could easily express these terms in the frequency domain. So let us do that. Okay. First is this g of t. Okay. Although you could see the amplitude is 1 by ts. Okay. 1 by ts times g of t. The second one will be similarly 2 by ts times g of t cos omega st. So these things could be displayed in the spectrum. So let us display it. So the spectrum will be like this. So g of t will appear here. This is 0 and this is your g of t. Okay. So this is your g of omega. Okay. This whole spectrum that I am drawing is your g bar of omega, because this is the sample signal. So g of omega will be here. Okay. Then the next is g of omega minus omega s. So it will be somewhere here. Okay, omega minus omega s. So g of omega plus omega s, it will be here, right? Similarly, g of omega plus 2 omega s, it will be here. Sorry, minus 2 omega s. G of omega minus 2 omega s will be here. That means g of omega plus 2 omega s will be here. In this way, this spectrum would go on up to infinity. Okay, so this will go on up to infinity. The amplitude here is 1 by ts times. Okay, so somewhere it will be 2 by ts, somewhere, so it will be different. Huh? So, however, you could see the spectrum would look like this. Okay, now there is something special here. We have to understand that. Now we have already discussed that the sampling frequency fs should be greater than or equal to 2b. Okay, or so if we like take three different cases. Okay, we can take three different cases here. One could be your fs is equal to 2b, one is your fs is less than 2b, and one is fs is greater than 2b. So for these three cases, okay, we will have this spectra in three different, will be shown in three different ways. Okay, this spectra will look different when the relationship between these frequencies is different. Okay, let's see. First is the case when your fs is equal to 2b. Okay, fs is equal to 2b. That means the spectra would look like this. This is your g of omega. Okay, so here we have, see, fs is equal to 2b means whatever this is the bandwidth. Okay, this fs will be exactly the double of that, exactly the double. Okay, exactly the double means it will be exactly here, just near it, omega minus omega s. This is g of omega plus omega s. Again, g of omega minus 2 omega s, here g of omega plus 2 omega s. So this way, this will go on up to infinity, and all the spectrum will be like this side by side. Okay, because why they are adjacent to each other, exactly adjacent, because fs is equal to 2b. So that's why you see, if this is b, okay, this is b, so this is c, 2b, right? So that's why fs is equal to 2b means exactly it will be located here. Okay, so now next case where fs is less than 2b. Okay, so if fs is less than 2b, the spectra would look like this. This is your g of omega. Okay, and this is b. Okay, that means in dotted line I can show you that 2b should be somewhere here, right? If this width is b, okay, and this width is also b, then 2b is somewhere here. But you have taken a sampling frequency fs which is less than 2b. Less than 2b means it will not be here, it will not be here, it will be somewhere, it will be smaller. It is not 2b means it is less than 2b means this will be somewhere here, not exactly here, it will be somewhere here or here. It could be in any of these places. So if it is in any of these places, the spectrum would look like this. Okay, so this is your g of omega minus 2 omega minus omega s. Okay, similarly g of omega plus omega s will be like this. Similarly, the next one will be like this. So they will be, the spectra will be overlapping like this. Okay, that is the problem. Now similarly, if we take fs is greater than 2b, fs is greater than 2b, so how the spectra will look like? You see here, this is your g of omega. Okay, then this is your bandwidth b, this is the bandwidth b. That means 2b is here, b, another b, this is the width na, b and b, that means 2b, this is the 2b. But you have taken fs is greater than 2b. Greater than 2b means it will be the spectra will be, the midpoint of the spectra will be somewhere here, or it could be here also, it could be here also, it could be here also, it will be far away from that. That means the spectra that you will be drawing, there will be gap between this spectra, it will be like this. So this is your g of omega minus omega s, this is g of omega minus 2 omega s. On the other side also we will have the same gap, g of omega plus omega s, g of omega plus 2 omega s. So the spectra would look like this. Okay, for these three cases. Okay, now there is something else we have to understand also. So this is the sampled signal, as I have told you that this is this total spectra that you see here is the g bar of omega, that is the sampled signal. Okay, g bar of omega. Now when we are reconstructing the signal, we have to get back our original signal, which is your g of omega. So here you see, this is the sampled signal, that whatever you see here, whole highlighted signal is the sampled signal. Now within this sampled signal, when we are reconstructing the signal, we should get back the message signal. Which one is the message signal? Can you tell me which one we want to get back? Any one of you?
GFT.
G of t is the original signal that we want to recover, right? So that is what we want to recover, this g of t, because when g of t was sampled, we get this whole yellow highlighted signal. Okay, so when we reconstruct a signal, our aim is to get back this g of t. Okay, so in this spectra, you could easily see which one is g of t. Yeah, g of omega is the actual signal that is the Fourier transform of g of t. So that means this is the signal that we want to recover. So if you use an ideal low pass filter, a low pass filter which will be having a frequency response something like this, you will be able to recover it, right? Now just see the three cases. Okay, see, if your fs is equal to 2b, you would need an ideal low pass filter. If your fs is less than 2b, even if you use an ideal low pass filter, you will never be able to recover your original signal. Okay, because the spectra I have overlapped into each other, and even if you try to filter it, you cannot, you will see that this interference has crept into it, and there is no way you could actually do away with the interference. So some interference is also there, and along with it you could see that a part of the signal is also missing. Okay, so there is no way you could recreate a signal which is sampled at a rate fs less than 2p. Okay, now if you would sample the signal at a rate fs is greater than 2b, you could always use a filter with gradual cutoff. You don't need an ideal low pass filter. Okay, so now you could compare and see that why I had told you in the beginning that we should take fs as greater than 2b, because when you take fs is greater than 2b, you could easily see that the spectra doesn't overlap into each other. There is a gap between this between this subspectra, and we could use a low pass filter with gradual cutoff. Okay, it is actually impossible to make a ideal low pass filter practically. Okay, so you should use a filter a gradual with gradual cutoff. So if you want to a filter with this gradual cutoff, you have to follow this condition, that is fs is greater than 2. Okay, and this is also the proof of the sampling theorem, that why you should sample the signal at a rate fs greater than equal to 2b. Okay, if your fs is greater than 2b, then at least theoretically you are able to get back your original signal by using an ideal low pass filter. But if it is less than 2b, as you see in this case, okay, you cannot get back your original signal. Even theoretically also you cannot get back your original signal. Achha, however, one thing that you could note here is that the strength of the signal is reduced here, na? 1 by ts. Okay, the strength of the signal is reduced by 1 by ts. So normally the low pass filter that we use, it should have a gain of ts. So if it has a gain of ts, then ts multiplied with that 1 by ts, okay, it will be normalized, or it will be equal to 1. Okay, so let us again discuss, just once go through whatever we discussed now. Okay, let me just review it. Okay, so that if anyone has not understood anywhere, he or she can catch up with it. Okay, so we have already discussed what is sampling. Okay, so sampling is basically a process that converts the continuous time signal to discrete time signal. That is the job of sampling. Okay, job of sampling is just to convert continuous time signal to discrete time signal. That's all, nothing else. Okay, however, we should sample the signal at a sufficient rate. Okay, if you do not sample the signal at a sufficient rate, you cannot reconstruct it when you are converting that digital signal to analog. Okay, so there is a rule that we follow to sample a signal. That rule is your sampling theorem. And what does this sampling theorem say? The sampling theorem says that a signal whose spectrum is band limited to capital B Hertz, okay, can be reconstructed exactly without any error from its samples taken uniformly at a rate capital R, which should be greater than equal to 2B Hertz. And this is theoretically, and practically you should sample a signal at a rate capital R, which should be always greater than 2B Hertz. Okay. Now, why we should take that minimum rate capital R, or why we should take a minimum sampling frequency as fs is equal to 2B Hertz. So in order to do that, we have to prove the sampling theorem, and in order to prove the sampling theorem, we have taken a signal g of t, and that signal g of t is band limited to B Hertz. This is that g of t. Okay, now sampling that g of t at a rate fs Hertz, okay, and this can be done how this can be done? By multiplying the signal g of t by a impulse train. Okay, so that is what we did. We multiplied this signal g of t was multiplied with this impulse train. So once we multiplied this impulse train with this impulse train, we got a signal like this. We have named it g bar of t, and g bar of t is what? Your multiplication of g of t with the impulse train is g bar of t. Okay, so we could also write that in this form: summation of n g of nts multiplied with del of t minus nts. So that means shifted impulses are there, and each impulse is having the amplitude g of nts. Okay, so now you could see that delta ts of t is a periodic signal of period ts. Okay, we have already seen this. So we have tried to find out the Fourier series of it in order to expand it. Okay, the Fourier series is in this form: 1 by ts times 1 plus 2 cos omega st plus 2 cos 2 omega st plus 2 cos 3 omega st, in this way, dot 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 dot. Okay, so now we replace this delta ts of t, okay, with this Fourier series. So once we replace it, we would get this equation. Okay, g bar of t is equal to g of t multiplied with delta ts of t, which is equal to 1 by ts times g of t plus 2g of t cos omega st plus 2g of t cos 2 omega st plus 2g of t cos 3 omega st. So one thing that you could observe here is that in the sampled signal itself, we are having the baseband signal g of t. Although its strength is reduced to 1 by ts, but we are having our baseband signal along with some harmonics. These are some of higher frequency signals or harmonics that are also present in the signal. So that means your baseband signal plus some harmonics is the sampled signal. So now what we try to do is we try to express this signal in the terms by taking its Fourier transform. We try to represent this in the frequency domain. So if you take the Fourier transform of this, okay, you could always show this. So g of t will be shown like this. Okay, g of t cos 2 omega st will be here and here. Similarly, g of t cos 2 omega st will be here and here in this way. Okay, so they are present here. Now we have actually three different cases that we can take here. One is your fs is equal to, although by the sampling theorem, although the sampling theorem suggests that you should sample at a rate fs greater than equal to 2b, but we could actually test for three conditions, and those three conditions are fs is equal to 2b, fs is less than 2b, fs is greater than 2b. So that we could take these three conditions and test and see which one is better. Okay, so first we take fs is equal to 2b, and you could see that the spectra is exactly adjacent to each other because we have taken fs in such a way. Fs is equal to 2b, so this is b, this is b, and that's why this is 2b, and the spectra is present here. Okay, so there is no overlap here, they are adjacent to each other. Then similarly, when we took fs is less than 2b, we could see that the spectra overlap into each other. Okay, similarly, when we took fs is greater than 2b, we found out that there is a gap between the spectra. Okay, between the subspectra, we could see a lot of gap is there here. Okay, so in order to like recreate this signal, we have to pass the signal through a low pass filter, because you see we have already seen that our sampled signal consists of our baseband signal along with some other harmonics. So if we could filter out the other harmonics, we could always get back our original signal. Okay, so that's why we pass it through a filter, so through a low pass filter. So if you want to use a low pass filter for your fs is equal to 2b, you need an ideal low pass filter. Okay, which is practically impossible to construct. Similarly, when you take fs is less than 2b, even if you use an ideal low pass filter, you cannot cover back your original signal because the spectra has overlapped into each other. Similarly, if you take fs is greater than 2b, then you could always use a filter with gradual cutoff. You don't need an ideal filter. Since you need a filter with gradual cutoff, you could always make such a filter. So it is quite easy to recover the signal if you are sampling it at a rate fs is greater than 2p. Okay, so this also proves the sampling theorem, which we have already discussed.